Who wouldn't want to see a robot that can jump higher than any human? Does this sound too good to be true? Well, it's here. The world's highest jumping robot can jump up to 100 feet. Did we get your attention now? Well, let's get straight into the video. In today's video, we will reveal the record-breaking robot that jumps up to 100 feet. And you won't believe how small this robot really is. The Elliott Hawks jumping robot. Many times, when engineers are trying to develop robots that can navigate difficult real-world conditions, they go to animal species for inspiration. This type of biomimicry has resulted in the creation of robots that can run as quickly as cheetahs or dogs, or hop as quickly as birds take off into flight. However, researchers at the University of California, Santa Barbara have recently accomplished groundbreaking work by circumventing the limitations of biological models. Their 30-centimeter tall jumper has the potential to launch itself more than 30 meters into the air, which is equivalent to roughly the height of a 10-story structure and 100 times its height. This gravity-defying performance is light years ahead of anything that any live organism could hope to do in terms of distance. According to Elliott W. Hawks, a mechanical engineer at the University of California, Santa Barbara, and the lead author of a study detailing the Super Jumper project, the best animal jumper is likely a squirrel-sized primate called the Galago, which has been measured jumping around 2.3 meters high from a standstill. The Galago is a primate about the size of a squirrel. In the past, combustion has been used to launch jumpers to heights of 8 meters, and compressed gas has driven them to reach heights of 10 meters. He adds that the device also stands out in the mechanical field, where previous jumpers have reached heights of 8 meters and 10 meters respectively. According to Sarah Bergbreiter, a mechanical engineer at Carnegie Mellon University who was not involved in the new study but provided an accompanying remark on it, it jumps significantly higher than most of the rest of the jumping robots in the world do, if not all of them that I'm aware of. How does this robot work? The team responsible for designing the new Leaper extensively used elastic power. In this type of jumping system, a component known as an actuator moves and stores energy in a spring. A latch then releases the energy to launch an object into the air. This fundamental mechanism is comparable to those utilized by members of the animal kingdom. For instance, the leg muscle of a grasshopper acts as an actuator. When it contracts, it bends back a spring-like part of the grasshopper's knee joint to create tension. This tension is then released to propel the grasshopper's jumps. However, in the context of the new project, human engineering contributed to several significant innovations. The maximum height that any elastic-based jumper may reach is determined by the amount of energy that the spring can store, which in turn is determined by two different factors. The first consideration is how much work can be supplied by an actuator. In animals, each muscle only has one contraction available, which limits the amount of spring that may be stretched. However, in the new mechanical jumper, the researchers decided to utilize a motor as the actuator since it could turn numerous times before each jump and hence continue to store a greater amount of energy. The capacity of the spring to store as much potential energy as it can without significantly increasing its overall mass is the second component that contributes to the effectiveness of an elastic jumper. The researchers developed a 30-gram device whose entire body functions as a spring to achieve the highest possible energy density with the new bot. What is the Elliott Hawks jumping robot made of? Rubber bands and slats made of carbon fiber, which have a far higher energy density than biological tissues, make up this component. When the actuator, a lightweight rotary motor, rotates, it winds up a string that constricts the spring. This places the rubber bands under tension and compresses the carbon fiber, bending each slat into a curved configuration similar to an archer's bow. The lock is then released, which causes the bot to be launched into the air at a speed of approximately 100 km per hour, acting in a manner not unlike an arrow that propels itself. What can this robot do? This robot can throw itself over buildings and may be able to navigate several typical situations more effectively than wheeled, walking, or even flying designs, which these environments may hamper. Bergbreiter observes that jumping, in some sense, is a wonderful way of getting around, because you can jump over obstacles that might be in your path. On the other hand, you don't have a lot of the complexity that comes from trying to fly over those obstacles or navigate around those obstacles with legs, he says. Hawks is particularly enthusiastic about the prospect of developing jumping bots for use in space exploration. He explains that his device has the potential to travel even greater distances in environments with low gravity and no atmosphere. On the moon, our device could theoretically leap forward half a kilometer while going 125 meters high in a single leap, he says. This would be accomplished in a single bound. For example, it may plunge into the depths of a crater, or hop up the edge of an impassable rock, collect samples, and then return to a wheeled rover. Is this jumping robot ready for use? The device is undergoing further development thanks to Hawks' collaboration with NASA. However, the jumper must undergo additional development before it can reach its full potential. For example, the current prototype cannot navigate independently. Additionally, the motor is powered by a battery, and reloading the spring between jumps takes a few minutes and a couple of minutes respectively. And perhaps most significantly, it cannot regulate the height of its jumps. Despite this, Hawks anticipates that over the next 5 years, a more advanced variant will be ready for launch. The new technology, on the other hand, can aid scientists even if they never have to leave the planet, because it demonstrates the boundaries of biomimicry. The ability to examine how animals and humans alike launch their bodies into the air is one of the primary motivations behind the creation of many different types of jumping robots. Consequently, they consider the constraints imposed by those creatures. Yet, this experiment demonstrates that they are not required to do so, and that breaking some norms might result in significant benefits. How successful is the Elliott Hawks jumping robot project? According to Hawks' explanation, biological systems work under different restrictions than designed systems, which means that a perfect solution in biology is not always a perfect solution in engineering. Rather than merely replicating a solution that can be found in nature, it is vital to understand how a particular manufactured system has comparable and different restrictions than a model biological system. The fact that this strategy was successful suggests that it may be modified to construct different agile machines that could be used in a variety of contexts. Bergbreiter agrees, "We do not have to engineer systems with the same limitations that biology has," she says. Just like planes don't have wings and cars don't move. Because of the various assumptions and constraints we bring to the table when designing systems, we can take very different approaches. Well guys, we've come to the end of this video. Do let us know your thoughts on this jumping robot using the comment section below. If you enjoyed the video, do drop a like and hit the subscribe button for more of our updates.